So welcome everyone. We have another ITMP seminar, and today we are happy to have Alberto Salvio, and he will talk about models for reverse energy range, particles, mid-gravity, and cosmology. Please start.
Thank you very much for inviting me to give the seminar. It's a pity I cannot be there in person, but okay, this is better than nothing. So my talk will be about this topic, models for a vast energy range, and it will be based mainly on this series of papers. There are some in collaboration with other researchers, like this one with Hardy Vermeer, another one with Anish Ghoshal, and the last one with Simone Scollo. So first of all, so what do I mean with models for a vast energy range? What I mean is that I'm talking about models that are valid from the Hubble scale up to the Planck scale. And let's start with some motivations for considering these models. So this is a first general slide about the fact that the standard model is in agreement, at least so far, with all experiments performed at CERN. Let's say there are no ambiguous signals of physics beyond the standard model. And in 2012, the last standard model particle was discovered at CERN, the Higgs boson. And with that, we also know that there are other forces that were predicted by the standard model, which are the Yukawa interactions beyond the strong electroweak forces and gravitational forces. However, the standard model needs to be extended. We know this for sure. One reason is the presence of neutrino oscillations. And for those, we actually have a quite obvious candidate, which is the right-handed neutrinos, and but there are, of course, other candidates. The second point that allows us to say that the standard model needs to be completed is dark matter, because there are no dark matter candidates in the standard model. And finally, we want a theory that is able to quantitatively reproduce the baryon asymmetry of the universe. So many ideas have been proposed to address all these problems and other problems of the standard model that I will discuss about later on, but it's difficult to find scientific criteria to select the right path because there are so many models where I cannot choose among them. This is one of the reasons why I'm interested in these models for a vast energy range, because one can reduce the ambiguity in the model building by requiring that not only the experiments at colliders should be in agreement with the theory, but in fact all experiments and observations, including those of cosmological and astrophysical nature, should be satisfied. I mentioned before other problems of the standard model, besides those that I've already mentioned. One of these, which is rather than a problem, a potential problem of the standard model, because of some reasons that I'm going to discuss now, is the fact that the electroweak vacuum is metastable. So in this line here, I show you that the top mass, MT, has to be smaller than a value which has been computed by these researchers, myself included, in 2013, which is in slight tension with the central value, which is now available, for example, in the particle data group at the 2 sigma level. So this is not much, but one can start thinking about what would be the implication of living in the metastability region, say in the region in which the electroweak vacuum is not absolutely stable, but its lifetime is larger than the age of the universe. This is the metastability region depicted in the plane MH, the Higgs mass versus M top. And this green region is the stability region. And then there are the pathological region of instability and non-perturbativity, which corresponds to having Landau poles below the Planck scale. And we actually live extremely close to the border between stability and metastability. If we zoom in, we see this little tension to sigma level, but the remarkable fact here is that we live so close to the border. So just to give you some ideas of how to compute the probability of vacuum decay, if we leave, so if there is a metastable situation, then there is a false vacuum, which is the standard model one, and then there is the true vacuum, the one which has smaller potential, and we can compute the probability of vacuum decay, that the standard model vacuum decays into the true vacuum. This has been, the formalism to address this question has been developed by Coleman and Callan in the 70s. And the probability gamma per unit of time and volume of creating a bubble of true vacuum within a space volume dV and time interval dt is given by this expression, where SB is the so-called Euclidean action of the bounce of size R, which is related to this quantity appearing here by this relation. And the bounce H is an SO4 symmetrical Euclidean solution of the equations of motion of the Higgs. Here, V is the potential of the Higgs. And also importantly, one has to keep in mind that this equation has to be solved with this condition. The first one is a regularity condition, and the second one is the physical condition that tells us that we are looking for a vacuum of true, a bubble of true vacuum within a space filled by the false vacuum. Okay. So first question we can ask is whether metastability is a problem during inflation. Oops. And so first, quickly, let's review what inflation, what are the main properties of inflation that will be used later on. Okay, inflation solves the horizon, flatness, and monopole problems, but in order to solve these problems, it has to last enough. So there is a lower bound on the number of E-folds, defined by this equation where A is the scale factor and Tn is the time of the end of inflation, and T is the time at the beginning of inflation. This is implemented by some scalar field, which has a quite large but flat potential, such that the Hubble rate changes very slowly, and we have an early exponential expansion. And when these parameters, epsilon, eta, are very small, we can perform the so-called slow roll approximation, which simplifies a lot the calculations, and we end up with this formula for the inflationary observables that are the scalar amplitude, AS, its spectral index, NS, and the tensor to scalar ratio, R. Okay, I don't think I need to, so this scalar amplitude is the amplitude of the curvature perturbation, and this AT is the amplitude of the tensor perturbations in cosmology. Okay, so what turns out is that the metastability is actually a potential problem during inflation, because during this epoch, the energy were so high that transition to the true minimum were possible. And so you can obtain interesting upper bounds on the Hubble rate during inflation, as we found in 2017. And a second point that I want to make is that the condition to have standard model Higgs inflation is very similar to the stability bound, being computing this bound in 2014, and I found a bound very similar to the one I showed you before. So with similar tension with respect to the observed value of M top. And then if this is true, this means that you need at least another scalar field to trigger inflation. And this means that you need some physics beyond the standard model. However, let me stress again that we are not sure that we live in a metastability region because, as I showed you before, we just have a 2 sigma tension. But we can, let's say, use these bounds and these calculations to make further tests of the standard model, this time at very high energy compared to those colliders. And so these tests represent some complementary tests with respect to those performed colliders. So let's take now the standard model and nothing else. And we have, so in the Lagrangian, we have the Einstein-Hilbert term, the standard model Lagrangian, and then, which is minimally coupled to gravity. And then we have a non-minimal coupling between the Higgs doublet H and the Ricci scalar R, with some coefficient, which is called the non-minimal coupling, because this is a non-minimal coupling, which I call psi H. And then the result of our calculation was that we have this plot with psi H here in the horizontal axis and the inflationary Hubble constant H in the vertical axis, normalized to H critical, which is basically the scale at which you see the instability. So basically, this instability, or more precisely, metastability, occurs because when you consider the randomization group flow of the quartic coupling of the Higgs, you see that this quartic coupling becomes negative at some critical energy, which in the randomization group has to be basically identified with the field value. And this critical field value I call HCR here. So the green region is the region where we have no problem. So there are values of psi H such that there are no problems. But interestingly, we get some bounds on psi H from the metastability of the electroweak vacuum. In particular, we cannot live in the red regions. Okay, so as we have in the case of collider bounds, we get some bounds on the fundamental parameters of the standard model in this case as well, because this psi H has to be considered as a fundamental parameter of the standard model. In fact, we cannot avoid introducing this parameter, because if we don't introduce it, it is nevertheless generated by quantum corrections.
Excuse me, okay. Can I ask about the value of psi H? Because in Higgs inflation, people say that they need psi H of order of 10 to the 4, and you have on your graph something like 0.1. So can you comment why is differences so large? Or yeah, I didn't understand something probably.
So this is, first of all, so what you're talking about is Higgs inflation, right?
Yes. That people,
okay,
for Higgs inflation, you need a very large psi H. So you do not consider Higgs inflation, right?
I don't consider Higgs inflation because in order for Higgs inflation to occur, you have to basically be in the stability region or at the border between the metastability and stability region. So what I'm doing here is something different. I'm deep in the metastability region, so I do not consider Higgs inflation, and so the inflaton is played by some other field, and and then I see the constant.
But nevertheless, you add a non-minimal coupling. Nevertheless, you consider.
Nevertheless, I add the non-minimal coupling. Yes. Yes.
Okay.
Okay. So other problems of the standard model are so-called fine-tuning problems. Some parameters of the standard model within Einstein gravity are mysteriously very small. And these are the cosmological constant problem, the Higgs mass problem, and the so-called QCD theta angle problem, which is better known as the CP, strong CP problem. So the cosmological constant problem is the problem of explaining why the cosmological constant is so much smaller than all other scales present in the theory, in particular the Planck scale, but also other masses in the standard model. And it's fair to say that there are no universally accepted solutions. A possible way of addressing this problem is through anthropic considerations, as Weinberg pointed out in the 80s. However, in order for this to make sense, you need to construct a multiverse, which makes everything very much complicated. The Higgs mass is different because in this case we have dynamical solutions, let's say solutions that are based on symmetry principles. At the same time, it is also possible to address it through anthropics. And yet another different situation is for the strong CP problem, which is slightly different with respect to the other two problems. The Higgs mass problem, in a sense, is similar to the cosmological constant problem because it is the problem of explaining why another dimensionful quantity, the Higgs mass, is so much smaller than the Planck scale. The strong CP problem that I'm going to illustrate in the next slide regards a dimensionless quantity that I'm going to introduce in the next slide, rather than a dimensionful quantity. Another difference is that there are dynamical solutions, but not known anthropic solutions for this problem. So one logical possibility is to try to address the strong CP problem in some simple models, neglecting the cosmological constant, the Higgs mass problem, invoking for them the anthropic principle. Of course, it would be better to have a theory which, from a very simple theory, which from first principle explains everything, but we cannot do everything. So in the next slides, I'm going to focus on the strong CP problem. Okay, so what is the strong CP problem? One can add the following term to the QCD Lagrangian, which breaks both P and CP. It has some coefficient theta, and here G mu nu is the gluon field strength, and G tilde mu nu is its dual, defined by this equation. And then one important thing to notice is that the theta term has a physical effect only in the presence of quark masses, because if there are no quark masses, I can redefine the theory, redefine the fields of the theory in a way that this theta disappears, but field redefinition cannot affect the physics. So theta term has only a physical effect in the presence of quark masses. And one physical effect in the presence of quark masses is to give a contribution to the electrodipole moment of the neutron, which is given here basically in order of magnitude, where m pi is the mass of the pion and MQCD is a typical scale of strong interactions. And we have a contribution of this order of magnitude. So from the observational bounds on the neutron, we get an upper bound on theta. And the strong CP problem consists in explaining why theta has to be so small, essentially. So one of the possible way of addressing this problem is through the so-called Petroglyn symmetry, in which one promotes theta to a dynamical variable such that changes in theta are equivalent to redefinitions of the various fields and so have no physical effect. And the way Peche and Quinn implemented this idea is through a global chiral U1 symmetry called the Peche-Quinn symmetry, such that some colored fermions are charged. And these colored fermions can be fermions of the standard model or fermions beyond the standard model. But in any case, because of chiral anomaly, a field redefinition leads to a shift in this coefficient theta. And at the same time, we know, as I said before, field redefinitions cannot affect physics. So any value of theta is equivalent to the P and CP conserving value. Okay, the second point is that we need to introduce some fermion masses because, as I said before, we are dealing with colored fermions, so we need to have them massive in order to satisfy the experimental bounds. And so the condensing field, which gives mass to the fermions, is charged under the Petroglyn symmetry. And so the U1 Petroglyn symmetry has to be spontaneously broken. This leads to a Goldstone boson, or more precisely a pseudo-Goldstone boson called the axion. It's a pseudo-Goldstone boson because the symmetry is actually not exact, but it is broken by anomalies. And this gives some mass to the axion. Okay, so let's see how to construct a simple, motivated phenomenological completion of the standard model, keeping in mind these problems. So one example that I proposed in 2015 and I've recently extended is constructed from the standard model by adding some right-handed neutrino sector, Ln, which is basically a type 1 CSO sector. You can see here, and I is the represented neutrino fields, and Mij are the Majorana masses, and this Yij are the Yukawa coupling between the sterile neutrinos and the lepton doublet and the Higgs doublet. On top of that, also added an axion sector, which is taken from the so-called KSVZ model, in which we have an extrascalar field, which is complex, one component, then two Weyl fermions, Q1 and Q2, with some Yukawa coupling with A, and then there is a potential, which is a quartic potential for A, and some portal interaction between A and the Higgs field. Here we have a Mexican hard potential, actually, which triggers the spontaneous breaking of the U1 Petroglyn symmetry through this constant Fa, which turns out to be also the axion decaying constant. One interesting thing of this model is that the non-minimal coupling between H and A allows to stabilize the electroweak vacuum, so makes the theory also theoretically more interesting. And at the same time, we can also explain the neutrino oscillations, or account for the neutrino oscillation, account for dark matter, as we will see through the axion and or the lightest sterile neutrino, and also account for successful baryogenesis through leptogenesis. And all this can be obtained in a single model. Here I show you some part of the region of parameter space where you can have absolute stability. In this case, we have a potential which is more complicated than the one in the standard model because we have an extra scalar. So the stability condition is not just lambda h bigger than 0, but you have another stability condition. So in order to have the potential absolutely stable. And this region here represents a region where the potential is, the electroweak vacuum is absolutely stable. And at the same time, for these values of parameters that I consider here, you can also account for neutrino oscillations, dark matter, baryogenesis. And at the same time, you can have the Higgs as the inflaton. So let's discuss about inflation. So this model, of course, has to be extended by introducing some gravity part. And it was further studied by several scientists like Ballesteros, Redondo, Ringwald, and Tamarit, who propose a variant where the Majorana masses are generated by the vacuum expectation value of the extra scalar. And inflation can be triggered, as I said, by the Higgs, or by actually a combination of the Higgs and A, as shown by Ballesteros, Redondo, Ringwald, and Tamarit. And one thing I want to stress is about Higgs inflation, because as I said before, you can also have Higgs inflation living right at the border between stability and metastability, the so-called critical line. And if you do that, you have some advantages with respect to the normal Higgs inflation, because the parameter psi gauge can be actually of order 10. And so the, I don't know if you heard about this, but there is some scale of perturbative unitarity breaking, which is controlled by this psi-h. And if psi-h is very big, like 10 to the 4, 10 to the 3, as you have in normal Higgs inflation, the scale of perturbative breaking of unitarity is much below the Planck scale. But in critical Higgs inflation is basically almost at the scale of the Planck scale. And at those high energies, you need anyway extra physics to UV complete gravity. Okay, so the critical Higgs inflation has some advantages with respect to normal Higgs inflation. So this is a picture that shows you the randomization group running of the various coupling in the standard model. And we are in the critical situation. You can see it from the running of lambda h, which is the one in dashed green. You see that lambda h approaches 0 at very high energy scales up to the Planck scale. And the typical potential in this case is a potential featuring some inflection point, or more precisely, some quasi-inflection point. And a very interesting feature of this Higgs inflation is that the value of R gets enhanced so that we can hope to observe the consequences of this setup in future observation of the CMB. And in particular, I worked out the inflationary observables in this model, and I got some results that is in agreement with the most recent Planck results. But still R, here I quoted some value 0.01, but you can have it also a little bit bigger, like 0.004 or 0.05. And there is hope to observe actually primordial gravitational waves from this inflationary setup. So this slide basically shows you that the theory is a valid effective field theory up to the Planck scale and including inflation. Basically, this brown line represents the inflationary scale, which is the Higgs potential to the 1/4. And all this series of lines, you see there is a label n, labeling this line. This last one is n going to infinity, n is some integer. Basically, are estimates of the cutoff of the theory, looking at various terms in the effective Lagrangian. So what you have is that this non-minimal coupling generates some non-polynomial terms in the Lagrangian. So you can expand in the fluctuations delta hi around the background, and have an infinite number of terms from which you can read some infinite number of cutoffs, which are basically the coefficients of these terms, which have dimension of negative powers of energy. And the one which is bigger, is more restricted, is the one in which you take this n to infinity. But still, even in that limit, you see that the cutoff is definitely larger than the inflationary scale, which means that the theory is a good effective field theory to describe inflation and all the subsequent epochs in the evolution of the universe. Let's now turn to dark matter in this model that I call a new MSM. Basically, is the minimal standard model extended with axion and stellar neutrinos. This is a work in collaboration with my student, Simone Scollo. And in this extension of the standard model, there are basically three possible sources of dark matter. One is the axion, the other one is the lightest stellar neutrino, And another possible source of dark matter could be primordial black holes, because as I will talk about later on, the fact that the potential features an inflection point or a quasi-inflection point has been proposed as a possible mechanism for primordial black hole production. But as we will see, the potential of the Higgs does not have the right quantitative features to lead to primordial black hole production. So we will end up with a scenario with just the axion and the lightest sterile neutrino. So first, let's discuss the axion dark matter. Basically, to discuss dark matter, we have to discuss the way axions are produced. And to account for dark matter, basically, there are a couple of non-thermal axion production mechanisms. One is the misalignment mechanism, which was proposed by these authors in the 80s. And basically, it is based on the evolution of the axion field from time scale where h, the Hubble rate, was much bigger than ma, the mass of the axion, up to time scales where ma was much bigger than the Hubble rate. And a recent calculation given by these authors has provided us this formula for the ratio of the axion energy density to the critical density. H, as usual, is the normalized Hubble rate today. And as you can see, this axion abundance depends on Fa. So in order not to overclose the universe, in order not to produce too much dark matter, Fa has to satisfy some upper bound. And
excuse me.
Yes.
Which axion you mean? You're talking about the string axion, I mean?
I'm talking about the QCD axion.
QCD axion. Okay,
Yeah.
it's not the string theory, the one which came from a string theory.
No. Okay, no. Now I'm going to string decay, but this has nothing to do with string theory.
Yeah.
Okay. So one important point is that Higgs inflation features very high reheating temperature after inflation. There is reheating, and the maximal temperature that the universe reached is this reheating temperature, which is very high in the case of Higgs inflation, basically because the Higgs couples sizably to all standard model particles. So after inflation, the Higgs field starts oscillating and it decays into standard model particles quite easily. But this means in particular that the Petroglyn phase transition occurs after inflation in this case. So in the sense that at least the Petroglyn symmetry is restored after inflation, so then it's broken again after inflation. This is because Fa has to be smaller at least than 10 to the 11 GeV, because otherwise you would produce too much dark matter, okay? Which means that Fa is much smaller than the heating temperature. So after inflation, there is the Petroglyn symmetry, which is then broken. But this also means that there is another axion production mechanism, which is the decay of string-like solution in this type of U1 symmetric theory, which is spontaneously broken, which was also estimated in the KS-VZ model, which is the model of interest here by these authors. Another source of dark matter, as I mentioned, is the light sterile neutrino, N1. I call MS the mass of this light sterile neutrino. And as I will discuss now, this can contribute some sizable fraction omega s of omega dark matter, the ratio between the dark matter density and the critical density. Basically, so let's discuss now the sterile neutrino production mechanisms that are relevant for dark matter. Basically, can be produced through a mixing with the active neutrinos. I call this mixing theta. And this mixing can receive several contributions from the mixing parameters theta alpha 1 of N1 with the active neutrinos of any flavor. So alpha can range in this set, electron flavor, muon flavor, and tau flavor. And this theta is defined by this formula. So basically, there are two ways of producing sterile neutrinos. One is the so-called non-resonant production mechanism, which for a standard quark-hadron crossover transition for TQCD around 170 MeV gives this relation between ms, theta, and omega s. So fixing omega s, for example, omega s equal to 0.12, if you want to account for the whole dark matter through sterile neutrinos, this corresponds to a line in the ms theta plane. Another way of generating sterile neutrinos, producing sterile neutrinos, which is rather an extension of this non-resonant mechanism, is the so-called resonant mechanism proposed by Schiff-Fuller in the 90s, which, as I said, is similar to the Dodson-Withrow mechanism, but there is a resonant enhancement due to the primordial lepton asymmetry, which is introduced in this model. So you have yet another parameter, which is this lepton asymmetry. So in this plot, I give you the line I told you before, which corresponds to the non-resonant sterile neutrino production. And the region between this black line and this orange line corresponds to the full space of resonant sterile neutrino production, which, as I said, reduces to the case of non-resonant sterile neutrino production in the limit of 0 primordial lepton asymmetry. And these lines here, these dashed lines on top of the plot, corresponds to constraints given by X-rays searches, because this sterile neutrino, because it mixes with the active sterile neutrino, it can decay into X-rays plus other stuff. And so you can search for these sterile neutrinos by looking at X-rays in the universe. And the one on the bottom is a phase-space bound related to Pauli's exclusion principle, what is known as the Treiman-Gun bound, which is around 0.1, 0.2 keV. So from this plot, we learned that the loud region has a sterile neutrino mass around the keV scale, roughly, and a very, very small value of theta. These are plots that are generated from the previous one by varying the fraction of dark matter due to sterile neutrinos that I call XS. So the previous plot was for XS equal to 1, and now I reduce XS to smaller values, as you can see here. And in the model, the other source of dark matter is the axion, which means that for each value of XS, you get a value of FA. Here I'm quoting two values. One is one that I call FA, as before, and another one that I call FA miss plus string. And FA corresponds to the value of FA in case you neglect this string decay production mechanism for the axion, while FA miss plus string is the value of FA that you get if you include both mechanisms. As you can see, the second FA is always smaller than the first one because you have two production mechanisms. So basically, at the end, you get that FA has to be essentially smaller than 5 × 10⁻⁻10 GeV in this model. So you get a window for the QCD axion decay constant, which is between roughly 10⁸ GeV and 5 × 10⁻10 GeV. Okay, so in this plot also show some other bounds which come from structural formation. For simplicity, considering only the non-resonant case, because the case of resonant production is not very precise. And as you can see, the structural formation bounds, which essentially is due to the fact that an extra species, which is very light, the extra sterile neutrino, generates a free streaming, which affects the structural formation. And from there, you can get some bounds, some lower bounds on the MS. And as you can see, these lower bounds are quite stringent. So this is one of the reasons why the presence of the axion, in addition to the sterile neutrino, is a good thing, because the parameter space which you just have the sterile neutrino as that matter candidate is very much constrained. So as I said before, primordial black holes can also, in principle, account for at least a fraction of dark matter. And this is because primordial black holes may be generated if the curvature power spectrum has a peak of order 10 to the minus 2, and this peak can be in turn generated by some inflection point in the inflaton potential. And if you recall, the Higgs critical potential, the potential of the Higgs in critical Higgs inflation does have an inflection point. So you can search for primordial black hole production in this model. But notice that this 10 to the minus 2 is about 7 orders of magnitude larger than the value of the corresponding quantity, AS, 60 e-folds before the end of inflation, which, as I showed you before, is 10 to the minus 9. So you need 7 orders of magnitude of enhancement of this curvature power spectrum with respect to the value relevant for inflation. And in fact, you do have an enhancement. This is the potential of the Higgs at the critical surface by varying the coupling lambda HA between the Higgs and the exascalar. And here is the corresponding plot for the curvature power spectrum as a function of the canonical normalized Higgs field. And you see that you do have a peak, but it's quite small because it's just a couple of orders of magnitude larger than 10 to the minus 9. And even by varying in different ways these parameters of the theory, you always get a peak which is much smaller than the one required to produce primordial black holes. So the result is that you don't have primordial black holes as a source of dark matter. So this was the first part of the talk about simple motivated phenomenological completions of the standard model. And now we can ask whether we can take this kind of reasoning to the extreme and ask whether we can go up to infinite energy and how we can go up to infinite energy. This is because, as we have seen, requiring BSM models to hold from the Hubble up to the Planck scale removes some ambiguity in model building. And one can ask whether we can further reduce this ambiguity by requiring the theory to hold up to infinite energy. And the naive answer is no, because we cannot perform experiments up to infinite energy. But here, the important point is that the requirement to reach infinite energy is so strong on the theory that you can have some predictions of low energies. This is related to the fact that not all models can be UV completed. Okay, so you can get some information in the infrared. Here we have several scenarios. One possibility is that all couplings flow to zero at infinite energy, and you have total asymptotic freedom in this case, by definition, total asymptotic freedom. So this is a scenario similar to what happens in QCD, but in fact extended to all fundamental interactions. We are requiring that all couplings flow to zero. Or there's another possibility that the couplings flow to an interacting fixed point, which is the so-called total asymptotic safety. The first case is the one represented here on the left, the plot on the left, and the second one is the one represented in the plot on the right. And more generally, you can have that some couplings flow to zero and others to an interacting fixed points. In this case, you have a scenario that you can call total asymptotic freedom safety, TAFs. But these two scenarios, the second one and the third one, are quite complicated, technically speaking, because typically these interacting fixed points are at values where the couplings are non-perturbative. So you cannot use perturbation theory to be sure that you have a fixed point. So let's focus on the first case. Of course, you have a big problem here, because you know that Einstein gravitational interactions increase with the energy. And so you know that at some point, Einstein gravity becomes very strongly coupled at the Planck scale, roughly speaking. And the basic consensus is that Einstein gravity goes out of control, breaks down essentially at the Planck scale. So you have to consider theories that modifies this behavior of gravity at some intermediate energy scale, lambda g, such that the theory is reproducing Einstein gravity at the low energies, but it does deviate from it at the very high energies and eventually becomes very, very weak or soft. So this is the softened gravity scenario. There are some examples of softened gravity, like for example, string theory is an example, or some non-local quantum gravity, or theories where you add quadratic incurvature corrections to the Einstein-Hilbert action. But I'm not going to describe this theory in detail. From now on, I'm going to be quite agnostic about this hypothetical softened gravity theory. I'm just assuming that at some energy scale lambda g, gravity becomes soft. But there are interesting consequences of this paradigm. One is the fact that Landau poles have to be eliminated in order for all couplings to be totally asymptotically free. And this leads to a nice explanation of the electric charge quantization. And basically, we found just two options that are not severely constrained by proton decay. One is the so-called Patti-Salam gauge group, which we have as gauge group SU4 times SU2L times SU2 right. And another possibility is the so-called trinification gauge group, where you have SU3 color times SU3 left times SU3 right, which leads to some new physics at a scale which is not inaccessible at colliders. And in particular predicts new types of vector bosons and Higgses and so on. Here I give you some table which summarize the basic Patti-Salam model from the point of view of the field content and gauge group, the representation of these fields. You have extra spin 1/2, spin 0, and spin 1 particles. And correspondingly, here I showed you some summary of the field content and gauge representations in the case of trinification, which is even more interesting from some point of view than Patti-Salam, because you have also some right-handed neutrinos included in the theory. Okay, one thing you can ask now, since we talk about the axion in the simple bottom-up approach, whether you can construct a tough axion sector in this type of scenario as well. And in 2020, sorry, I have proposed a tough axion sector. This features two extra quarks, Q and Q bar, that are doublets of a new SU2 group that are called SU2A, plus one complex scalar A, such that we can write this Yukawa coupling and have a potential which is given by these three terms. The second and third term terms are quartic couplings, and the first one is a master. And there are values, infrared values of this lambda 1, lambda 2, and y that corresponds to total asymptotic freedom. Here, T is a way of parameterizing the energy of the renormalization group. Mu0 is some arbitrary energy reference scale. So when mu goes to infinity, T goes to infinity. And as you can see from the plots, all couplings go to 0. And these lambda tildes are basically T times lambda. And here I give you the fixed points, which are Gaussian in this case, for several values of a parameter that I call delta, which corresponds to the extra contribution due to the standard model sector to the running of the strong coupling GS, essentially. We have some unstable vacuum solution that has to be that are ruled out, and some stable vacuum solution that represent physical situations. And for those values, you get a prediction for lambda 1 and lambda 2 at low energy. And it turns out that also Y is predicted at low energies because if you put Y to 0, first of all, you don't get any tough solution. And only isolated values of not only lambda 1 and lambda 2, but also Y are compatible with total asymptotic freedom. So you get both the lambdas and Y predicted with low energies. Even better, you can also generate FA dynamically, quantum mechanically in this model by the so-called Coleman-Weinberg mechanism. So you start from a potential that has no dimensional quantity now. I just have the quartic couplings. And basically, FA corresponds here to the scale at which lambda 1 plus lambda 2 is equal to 0. Because at this point, as you can see here, you have a flat direction, which is A equal to A dagger. And so the radiative corrections can be bigger than the three-level contribution, and you can break dynamically the Petroglyn symmetry. Here I show you where how basically lambda 1 plus lambda 2 gets equal to 0 at low energies. And in this case, you get an even more predictive model, because not only Y and lambda 1 and lambda 2 are predicted at low energies, but also GA, the gauge constant of SU2A, gets predicted, because you have to fix a particular value of GA in order to satisfy this relation of a fixed energy. So basically, you have a model in which an axion sector, more precisely, in which the only dimensionless parameter is the GS, the gauge constant of SU3 color. And here I put an extra bar on top of it to say that this coupling is computed at the Petroglyn symmetry scale, FA. An interesting fact of this model is the fact that, as I showed in a paper with Anish Ghoshal, is the fact that you can have a strong first-order Petroglyn phase transition, and consequently, you can have gravitational waves that are within the reach of gravitational wave detectors. Here I give you some information on how to characterize this strong first-order phase transition. Basically, in this scenario, bubbles are created and diluted by the expansion of the universe, and they cannot collide until the temperature reaches the so-called nucleation temperature, which is the temperature at which the decay rate of the false vacuum here is of order of the Hubble rate to the 4th power. And an important parameter is the so-called inverse duration of phase transition, which is defined by this quantity. And it turns out that in Coleman-Weinberg symmetry breaking scenarios, because they are almost scale invariant, this beta is very, very small. And so the phase transition lasts a lot. So this is the reason basically why you have a strong first order phase transition in this scenario, basically because you trigger the breaking of Petroglyn symmetry through the Coleman-Weinberg mechanism. Here I give you a plot of Tn versus GS bar, so the QCD gauge constant, for different values of Fa. And here I give you the predictions for the gravitational wave spectrum as a function of frequencies. The predictions are the black lines for different values of GS bar and Fa. And the colored lines are the sensitivities of gravitational wave experiments. And on the right, I give you some summary plot of the region in the plane F peak, omega peak, predicted by the model. F peak is the frequency peak here, and omega peak is the value of omega gravitational wave, this exact gravitational wave spectrum computed at F peak. So from this plot, you can see that you can have a signal that is within the reach of gravitational wave experiments. Okay, let's summarize the talk. So standard model extensions valid in a vast energy range allow us to reduce the ambiguity we have in model building. And we have seen two approaches. One is a bottom-up one. And as an example, I mentioned the ANU-MSM model, in which we add to the standard model a simple QCD axion sector plus 3 right-handed neutrinos. And this remarkably can account for all the observational evidence for new physics that are at least experimentally confirmed, and solve at the same time the strong CP problem, have a absolutely stable electroweak vacuum, and can have Higgs inflation at the critical hypersurface. And at the same time, we show that we can have a multi-component axion sterile neutrino dark matter. Then there is a top-down approach, which is more ambitious, but one of the disadvantages, to be fair, compared to the other approach, is the fact that the number of degrees of freedom here gets very large compared to the simple bottom-up approach, as I showed you before in the table summarizing the extra fields present in the Patti-Salam and trinification models. But it is more theoretically appealing, and more importantly, it is more predictive than a simple effective Lagrangian approach, because theory with UV fixed points basically typically predicts values of parameters in the infrared as well. We have seen an example in the axion tough sector. And in this example, we have also discussed how the theory made basically, let's say, in the case in which Fa is generated a la Coleman-Weinberg, can also produce gravitational waves that are within the reach of gravitational wave detectors. Okay, thank you very much for your attention.
Thank you for a nice talk. Do we have any questions?
I have a question about softening of gravity. So basically, the question is, maybe I didn't catch the mechanism that you imply that will soften the gravitational coupling. Can you just repeat or explain? Do you have in mind some specific mechanism which makes gravity weakly coupled at above the Planckian scale?
You want me also to explain again what I mean by this, or only if I have in mind some particular mechanisms?
So you have in mind that the string theory is switched on, roughly speaking, and this picture is just effective picture, and it doesn't mean that you just do something with Einstein-Hilbert action and that's it. You mean that you include the entire string theory, right?
This was an example, because in string theory does basically this. It softens gravitational interactions at the scale which is slightly below the Planck scale, because it has to be slightly below, because if it is right at the Planck scale, the theory is already out of control. So it has to occur at least a bit before Planck scale. So string theory is an example of softened gravity.
Okay.
And there are other examples. I mentioned this possibility, the non-local quantum gravity, which is maybe is related to string theory. There are some authors that stress the analogy between string theory and non-local versions of quantum gravity. And another possibility is this gravity where you have, in addition to the Einstein-Hilbert term, some quadratic and curvature corrections. And in that case, you can also soften the gravitational interactions at a scale below the Planck scale. But from this point on, I didn't assume any of these mechanisms. I just focused on the matter sector, essentially.
Okay, thanks. And I also have a question about the effective Higgs potential. And you mentioned that it would be nice to have some multi-loop calculations of the Higgs potential, right? And I wonder whether they will be trustable given the fact that perturbation theories tend to if you included many loops, right? And Yukawa coupling is very large, so so how many loops can be taken into account and trust them to calculate the effective Higgs potential?
So you're mentioning the
beginning, the first
the
slides.
beginning of the talk where I talked about the metastability.
Yeah.
Okay. So the question is, how many loops I can?
Yeah. So right now, if you plot the Higgs effective potential in one loop, it is drastically different from the effective potential in two loops, and basically you cited the result in, I believe, 3 loops or something. Yeah, or 2 loops. I don't remember, but yeah. Looking at just the pictures, I wonder whether we are already in the regime when the perturbation theory diverges, and we cannot just hope to include an additional loop and the result will be better.
The point to keep in mind here, I think, is that we are extremely close to the border between the metastability and the stability region. So this is the reason why I think the multi-loop correction is relevant, because if we were right here in the middle, let's say, of the metastability region, so far away from the border between stability and metastability, then these multi-loop corrections would have no sizable effect. You see what I mean? So,
yes.
The multi-loop correction is a small correction. Perturbation theory does hold here, but the point is that we are so close to the border that even these multi-loop corrections give us sizable corrections. Not because they are large, because we are very close to the border.
So basically, the 2 loops are smaller than 1 loop.
The 2 loop corrections to the potential is small, but it has an impact here because we are so close to the border that even small corrections matter. You see?
Okay. Thanks. Thank you.
Any other questions? Okay, it seems that we don't have any other questions. So thank you very much for the talk, and thank you very much everyone for coming. And see you next time.
Thank you very much for the invitation. It has been a pleasure to give this talk. Thanks a lot.
Thank you.
Thank you.